Alright, welcome back everybody. This is the second video on Unit 3, Section 4 of AP Calculus, differentiating inverse trigonometric functions. In this video we're going to develop the rule for the arcsecant. We developed the rule for the arcsine and the arctangent in the last video and showed you all the rules. And then after we're done developing the rule for the arcsecant, we are going to do a couple of example problems using these rules. Alright, so here we go. Developing the rule for the derivative of the arcsecant. Much like when we were developing the rules in the last video, we're going to make y equal to the arcsecant of u, and then we're going to take the secant of both sides. So we've got secant of y is equal to u. And now we're going to go ahead and take the derivative using implicit differentiation, the derivative of secant of y, derivative of the outside, leaving the inside the same, makes it secant of y tangent of y, times the derivative of the inside, gives us dy dx. And that's equal to the derivative of u, which is just going to be du dx. And again, just like we've done in the past, we're going to multiply by the reciprocal of secant of y tangent of y in order to get dy dx by itself. Okay, now we want to have nothing but an expression of u in the denominator here, and we already know that secant of y is equal to u, so I know that I can replace this secant of y with a u, but I need to figure out what I can replace tangent of y with. Okay, so we go back to our identities, our Pythagorean identities. We've got that secant squared of y is equal to tangent squared of y plus 1. And so since I'm trying to replace tangent, I'm going to solve this for tangent. And we end up with tangent of y is equal to plus or minus the square root of secant squared of y minus 1. Okay, now here's where it's a little tricky for us from a thought process standpoint. We don't have, unlike the development for the arctangent, we don't have exactly what we need. And unlike the development for the arcsine, we don't have a real easy to define domain issue. But what we can notice, if you look at the four quadrants and you look at tangent of y and secant of y, and where they're defined, in all of the four quadrants, wherever tangent is positive, secant is also positive. And wherever tangent is negative, secant is also negative, which tells us that the product tangent of y times secant of y is always positive. Okay, so we need to make it so that the product of those two things is always positive. Okay, now tangent of y is this quantity plus or minus square root of secant squared of y minus 1. So we need to make it so that plus or minus square root of secant squared of y minus 1 times secant of y is always positive. And I'm going to actually go ahead and replace these with the u's. So we need to get plus or minus square root of u squared minus 1 times u to always be positive. And the mechanism that we can use in order to do that, okay, is if we get rid of this plus or minus, but we make it the absolute value of u instead of just u. Now, no matter what, whether u is positive or negative, this expression is always positive. So by putting the absolute value in here, we've kind of taken the fact that this is positive or negative and combined it with the fact that this is positive or negative to come up with a value that is always positive, just like we wanted this product to be because of the reality of the situation. And so I can replace secant of y times tangent of y with the absolute value of u times the square root of u squared minus 1. And that gets us to our derivative rule for the arcsecant. It's a little bit tricky, a lot more tricky than the other ones, but I'm never going to ask you to really replicate this proof. It's just a matter of you kind of having an idea of where it comes from. All right, let's go ahead and do some examples taking the derivative of these things. We're going to start with example 1. We're going to find the derivative with respect to x of the arctangent of x cubed. By the way, I did just notice that I forgot. There's a little something all the way at the bottom of the page here I forgot to mention. Good time to mention arcsine or sine inverse of x and arcsine of x are equal to one another. And that applies to all of the trig functions, the inverse trig functions. This does not mean this, even though this does mean this. Okay? So anytime you see that sine to the negative 1, that's always representing the arcsine. That's mathematical notational convention. If you wanted to write 1 over sine of x using a negative exponent, you would write it as this, sine of x to the negative 1. Although we never see that, because what is 1 over sine of x? Well, it's cosecant. Instead of writing this, we'll just write cosecant of x. Okay? So, anyway, sidetracked. All right, example 1. Find the derivative with respect to x of the arctangent of x cubed. So I'm going to apply my rule for arctangent. This x cubed is my u in my rule, and so my derivative is going to be equal to 1 over 1 plus u cubed. Or pardon me, 1 over 1 plus u squared. And since u is x cubed, that's 1 over 1 plus x cubed squared. And then I apply the chain rule, times the derivative of the inside. The derivative of x cubed is 3x squared. And so I simplify this. That's going to give me 3x squared over 1 plus x to the 6th. All right, first rule. All right, let's see what we got going on here in example 2. If g of x equals arcsine of x over 2, then the limit as x approaches square root of 3 of g of x minus g of square root of 3 over x minus square root of 3 is equal to what? You should recognize that this is the limit definition of g prime evaluated at square root of 3. That's what that limit represents, is it represents g prime at square root of 3. So we want to find g prime of x for this function. So I'm going to go ahead, g prime of x is equal to 1 over square root of 1 minus u squared. And then I apply the chain rule, take the derivative of the inside, the derivative of x over 2. Well, that's just 1/2 x, so the derivative of that is just going to be 1/2. And so g prime of x is equal to 1 over 2 times the square root of 1 minus x squared over 4. And now my value here is equal to g prime of the square root of 3. So I'm going to substitute square root of 3 in here for x. Square root of 3 squared is just 3. Makes this 1 over 2 times the square root of 1/4. Square root of 1/4 is 1/2. And bada boom, bada bing. The value of this limit should be 1. Okay. Next, example 3. If arc cosine of 3x is equal to the natural log of y, then dy dx is equal to what? Okay. So I'm going to go ahead and apply my inverse trig derivative rules. So this is going to be, let's see, the derivative of arc cosine of 3x is negative 1 over the square root of 1 minus u squared. Apply the chain rule, take the derivative of the inside, that's 3. And on the right-hand side, the derivative of natural log of y is 1 over y times dy dx, again applying the chain rule. And so I want to solve for dy dx. I get dy dx here by multiplying both sides by y. Gives me negative 3y over the square root of 1 minus 9x squared. Now, I would prefer, that's an okay derivative. In fact, that derivative probably works for me, but what I'm going to do is I'm going to actually get rid of the y so that I have dy dx just in terms of x. And the way I'm going to do that, I'm going to take this equation, and if I raise both sides of this equation e to that power, I get that e to the arc cosine of 3x is equal to y, and so I can substitute that in here. And I think I like this answer just a little bit better. Not a whole lot better, but just a little bit better. So there's two possible answers for dy dx there in example 3. All right, last one. Example 4. Find the derivative with respect to t of the arc cotangent of the cosine of t. So arc cotangent is going to be negative 1 over 1 plus u squared, so that's going to be cosine squared of t, times the derivative of the inside. The derivative of cosine of t is negative sine of t, and so this is equal to sine of t over 1 plus cosine squared of t. I don't see any good simplifications, so it looks like we're done. All right, folks, that takes us to the end of our lesson on differentiating inverse trigonometric functions. Go ahead and do some practice with these rules, get a little bit better at them, and hopefully you'll be an expert at them in no time. All right, have a great rest of your day, everybody. We'll see you next time. Bye-bye.